Hi, I am Jesús Pérez, professor at UNIR, Universidad Internacional de La Rioja, and it's a pleasure to be here with you today. I would like to thank the organizers of this Congress for giving me the opportunity to present my proposal for an easy-to-use open-source smart city platform. Today, cities face growing demands on infrastructure, public services, and environmental sustainability. As Balogun et al. In 2020 and Barona Garduño in 2024 pointed out, embracing digital transformation is no longer optional, it is something essential. By deploying modern information and communication technologies and processing vast streams of data in real time, municipalities can shift from gut-based to evidence-driven decision-making, boosting efficiency, transparency, and compliance with data protection laws. At the heart of this shift are open standards and shared frameworks. When cities adopt common protocols and data models, they dramatically reduce the technical complexity of integrating new sensors, platforms, and applications, lightening the load on often under-resourced IT team. Furthermore, as Wang, Xu, and Wu in 2024 and Durand-Reed in 2020 demonstrate, real-time dashboards and analytic tools empower municipal staff to optimize daily operations, from routing waste collection trucks to turning traffic signals, and to allocate scarce resources where they are needed most. Open government data then unleashes a wider ecosystem of civic apps in, let's say, mobility, safety, culture, and beyond, sparking innovation, stimulating the local digital economy, and reinforcing truly data-driven urban governance. Here we have three prominent open-source initiatives that provide key infrastructure components for a smart city platform, but stop short of offering a fully integrated vertical application ecosystem. The first one is Figware. Figware is an European-led effort to standardize context data management for urban environments. At its core sits the Orion Context Broker, which acts as a central hub for registering, updating, and querying real-time context information. A modular suite of enablers supports IoT device connectivity, big data historification, and dashboarding. Cities such as Santander and Seville in Spain, and networks like OASC have adopted Figware to break down silos, although they still need to build their own vertical services on top of it, which is a limitation. Snap4City is built directly on Figware. Snap4City extends the platform with streaming orchestration tools and semantic interoperability via the KM4City ontologies. This integrated IoT analytics suite simplifies the flow from device telemetry through complex event processing and into actionable insights. Pilots in Tuscany, Helsinki, and other European cities demonstrate its ability to accelerate prototype development, through each deployment often requires bespoke configuration, and that's the limitation of this solution. The last one is Centillo and CityOS. Centillo, originally developed in Barcelona, in Spain, is a lightweight sensor and actuator hub offering simple REST API to unify disparate municipal data sources. CityOS builds on top of Centillo by integrating it with CCAN for open data and Decidim for citizen participation, creating a municipal operating system, let's say. That's why the name of CityOS. While this architecture is fully open source and has been replicated elsewhere, it remains a reference model rather than a turnkey product, requiring significant local assembly and customization by each city. Although platforms like freeware and its peers offers foundations, they leave important gaps that limit practical use. The first one is the complex deployment and steep learning curve. Setting up and configuring all the modular components, let's say context brokers, connectors, databases, and analytics engine, can take weeks and demands skilled DevOps resources. Our municipality might not be able to obtain them. The second one is the lack of out-of-the-box vertical applications. Our cities must still build custom modules, for example, parking guidance, waste management, event ticketing, library applications, rather than simply enabling plug-and-play solution. They have to develop themselves the application. The third one is a weak data governance and multi-tenancy. Most existing platforms provide only basic API key or rule-based access control. There is no built-in support for hierarchical tenants, department isolation, or fine-grained audit trails. The last one is that each deployment requires its own dashboards, its own native applications to be developed from scratch, adding time, cost, and complexity for municipalities. I would like to highlight that over the past decade, we have seen ambitious field tests that pushed the boundaries of what a smart city could be, yet none became fully self-sustaining platforms. Here we have 4, but I will talk only about Smart Santander. Smart Santander proved that you can deploy thousands of IoT sensors in a real city, but long-term hardware maintenance and funding models weren't in place to keep it running after the pilot ending. So that's the reason why this field test ended. Now I would like to highlight the 4 key differentiators that set this platform apart. The first one is lightweight managed service and deployment in-country. By providing a turnkey managed offering that can be installed locally, we eliminate the need for cities to build and to maintain their own complex infrastructure. This not only accelerates time to value or time to market, but also ensures compliance with national data sovereignty and privacy regulations. The second one is a very important one, cloud agnostic architecture. By design, this platform does not tie cities to a single cloud provider. Instead, it leverages containerization and open APIs so that each municipality can deploy on AWS or Azure, whichever best meets their budget, performance targets, and compliance requirements. For example, if pricing or regional data residency rules change in a platform like AWS or Azure, cities can seamlessly migrate workloads between clouds without rewriting core services. And also, municipal IT teams can negotiate better rates by playing providers against each other and shifting non-critical workloads to lower-cost regions or spot instances. The third key differentiator point is the plug-and-play vertical modules. This proposal will deliver ready-made components for parking management, event ticketing, waste collection, and library services at the first version. each of them engineered for rapid integration. And our module roadmap is driven by, it's important to say that our module roadmap, let's say this parking management, event ticketing, waste collection, is driven by a citizen survey of 5,000 residents aged from 23 to 56. So every feature directly addresses today's most in-demand user-centric needs. And because the platform is open source, new verticals can be contributed and adopted by the community. The last key differentiator point is the reusable use of front-end libraries and mobile templates. To eliminate repetitive UI development, we provide a fully styled React style system components and native mobile templates for each module. This ensures a consistent, polished user experience across services, slashes development time, and also simplifies future maintenance or branding updates. Now, I would like to show you the reference architecture of this open source smart city platform proposal. The design is modular, as you can see, cloud agnostic, and designed for flexibility and scalability across different urban contexts. At the top of this diagram, we have the vertical apps layer. These are the citizen-facing applications, such as I told you, bus locations, smart parking, waste management, and ticketing for public festival or any kind of public event. All of these apps are built with React Native, ensuring consistent user experience across web and also mobile devices like Android or iOS. These applications communicate via HTTPS with our API microservices layer, represented here by Spring-based microservices. We have a gateway, and that gateway ensures secure access and handles routing and load balancing, while the microservice architecture allows for independent deployment of every feature and scaling out each feature too. We are using Keycloak for authentication and authorization. The data layer consists of a document-based NoSQL database, MongoDB, and Elasticsearch for powerful search capabilities. This dual persistence model provides both operational storage and analytical querying, what is essential for real-time and retrospective insights. Below that, we have the Edge services layer, which is key in a smart city context. It allows local processing close to the data source, for example, at the city or neighborhood level. Edge services support both HTTPS and MQTT, a lightweight protocol ideal for constrained devices and IoT scenarios like this one. On the bottom of the diagram, we see the actual IoT devices, let's say cameras, environmental sensors, temperature probes, and more. These communicate with the system either via MQTT or HTTPS, depending on their capabilities and constraints. Finally, I would like to repeat that this architecture is cloud agnostic. It can be deployed on AWS or Azure at this point, and this minimizes vendor locking and empowers cities to choose their infrastructure partner freely. In this slide, I am showing all the bibliographic references used to prepare this presentation. I would like to thank all of these authors, and thank you for taking the time to watch my video. And again, thank you to the conference organizers for allowing me to present this time.